Morning. Let's start. So today we will finish the slides from last time on MPI topologies, and I figured originally I thought we were going to do something new, but then thought it might be a good idea to go through the programming assignment handout. So we're going to do that after we finish the slides. Yeah. And there's a question yesterday or something on the exam. So we have an exam Wednesday, 3/26, which is about, I think it's 2 weeks from now, which is at the usual time, just 9:30 to 10:45. The topics are communication primitives, Pythonic and sample sort, embeddings, and dense matrix algorithms. So those were just the previous lectures, like after exam 1, and MPI will not be included, so you won't have to write any MPI code. And yeah, so I uploaded some practice exams on Canvas, and the procedure is just the same as the first one. You can bring one crib sheet front and back, just a regular size paper. And like if you look at the practice exams, there's a sheet of communication primitives and the runtimes. So you don't have to write those in your crib sheet. And you can if you want. But like for example, like just the thing that we had on the slide that was like a list of all the primitives and the runtime, like gather, reduce, all reduce, and so on. That will just also be on a sheet in the exam. So you can just use those directly in the questions. Any questions? Yeah, if you look at the practice exams and you have any questions, you can feel free to go to the office hours or post online. So we'll just continue with these slides on MPI topologies. So last time we ended at this example, but it was a bit rushed, so we can go through it again. If you remember, we were doing these Cartesian topologies in MPI, which is like you can define an arbitrary dimensional grid in MPI, and like you could always do this yourself with indexing. Like you know how many processors you have, and you can just do like, like row major indexing, for example. But it just makes, these are just like easier functionality, so you don't have to always do the indexing because it might be easy to get that wrong. It's just example usage. So in this example, there are 2 dimensions, and dims. So ndim is 2, and dims is the length of the dimensions, like how many processors are along each dimension. And in the beginning, we're going to fill these in. So first they start at 0, 0, because we don't know yet what the length will be. And just for illustration, this period, which is whether or not you have a wraparound link or not in that dimension, 1 means yes and 0 means no. Just for illustration, this is 1 and this is 0. And this is the coordinates. So for in the beginning, in like MPI COM world, you have a scalar rank, 0 up to p minus 1. But when you have a Cartesian topology, sometimes it's easier to express your rank in terms of a tuple equal to the number of dimensions that you have. So like if you have 2 dimensions, sometimes we talk about like Pij, which is the rank along each dimension. Sometimes it's easier to think of it that way. So that's what chords is. And this is the same. So we have init, which is just what you start always in MPI. We have com rank and com size, which are things that we have been using before. And now this is W rank, which stands for world rank, and com size, just the same as it is before. And dims create is this functionality that you pass in how many processors you have, you pass in the number of dimensions, and you get out a recommended length of the dimensions. So it'll tell you like how many processors you should put in the X dimension and the Y dimension in this example. So you don't have to you could always figure it out, I guess. If you have a square root number, it's easy. You could just take root p by root p. If it's rectangular, it's a bit more complicated to figure out how long the dimension should be. So this will just suggest you something. And this is just printing, if your rank is 0, then you just print out how long the dimensions are. And this one, MPI cart creates this Cartesian grid of the topologies. So you pass in the initial communicator, the number of dimensions, the length of each dimension, the periodicity, 1, and com. And this is the communicator that you get out. And com rank, so now you can get com rank from the new communicator and C rank, which is somewhere up there. Yeah, this C rank. So this is the scalar rank in the Cartesian grid, and you can get the chords here by passing in the communicator, the C rank, which is the rank in the Cartesian grid, the number of dimensions, and you pass in chords and it will fill it out. So chords is this array. And yeah, so often something that you want to do when you have a grid is you want to get something from a neighbor and you want to pass something to a different neighbor. So like you might get something in from the left and pass it out to the right, or get something from up and pass it down, or vice versa, whatever it is. So one easy functionality to do that, rather than doing all the index manipulation yourself, MPI provides this cart shift functionality that you pass in the communicator, which dimension you're interested in going along, the displacement, which is how far the neighbor is from you, and then an empty location for the source and the dest. And those are ints, or array of ints, because you're going to get one for each dimension. One neighbor in, one neighbor out, given your displacement, along whichever dimension you passed in. So here, this will get you your neighbor's one displacement along the 0th dimension. This one will get you neighbors of displacement 1 along the 1 dimension. And so, yeah, and it's important to remember that this doesn't actually do any data movement. It just tells you the index of your neighbor. Like we didn't pass in any, like when we do like send and receive, you have to pass in the buffers. This doesn't, or you have to pass in the buffers, the recipients, and so on. This doesn't take any buffer, so it doesn't actually do any passing. It just tells you where the passing is going to go. Once you do this, the next step is to do the passing. So we're going to go back up here, and this is the actual function that we're going to do. This was just setting up. So we have every processor has an array called sum, which has 2 entries in it. For now, it's 0, 0. It's just status. And there's 2 loops. So the outer one goes over the dimensions. So since we have 2 dimensions, first go over dimension 0, and second we'll go over dimension 1. And inside each dimension loop, we set some buffer in equals to 0. This is initialization. First we set in equals to 0 and out equals to C rank, which is our Cartesian rank. Then we go through the inner loop. For I 0 up to length of the dimension, this is dims j. We filled it out here. That's the length of the dimension. So first we start with j is 0 in the first iteration, so this is length of dim 0. Let's go through it. And everybody does send receive out. So we're pushing something out and we're getting something in. Out is this, our current rank. In is 0 in the beginning. And type is just int, destination, and source are what we got from cart shift. And in each iteration, we add what we got in to the sum and what we got out. And now we're going to put what we got in as what we got out. And we just keep going around. So in the first iteration of this inner loop, what we get in for everyone is just the rank of the incoming neighbor. And then in the next round, what we push out is this running total. Oh, sorry, no, we just push in the rank. We don't push out the total, we just push out the rank. Because out is equal to in the next round. Okay. And then so we repeat it equal to number of processors in the 0th dimension, and then we come back around and we repeat it for number of processors in the 1 dimension. And at the end, everybody prints out their rank, their coordinates, their neighbors, source and dest, and the sum that they got. And that's it. So what is this actually doing? Well, if we look at this example, let's say we have a 4x3 grid. So this is dim 0 and this is dim 1. And in 0, we had periodicity 0. or periodicity was equal to 1 along dim 0, and then periodicity was equal to 0 along dim 1. Here. Okay. So the actual ranks are like 0, 1, 2, 3, 4, 5, 6, 7, 8 in the, so those are the scalar ranks in the Cartesian grid. And the tuple ranks are like 0, 0, 0, 1, 0, 2, because dim 1 is going along this way. So it's increasing that way. And then if you look at this way, dim 0 is increasing. So 0, 0, 1, 0, 2, 0, 3, 0. And so what did we get as the sum? So this is like a lot, but if we just look at the first line, so the world rank was 0, the Cartesian scalar rank was 0, the tuple is 0, 0. The source and the dest along this dimension are 9 and 3, because we are here at 0, 0. What is coming in is 9, like this way, and what's going out is 3, that way. So that's source 9, out 3. Sum is 18, because what was this doing? We were passing along the ranks. So 9 passed itself here, so it became 9, and then in the same round, 6 passed 6 here, and in the next round, 6 passed 6 this way. And it repeated 4 times, so 9 plus 6 plus 3 is 18. So that's why sum is 18. And then if you look, we're going to do the same thing along dimension 1, but here there is no source because this is not a ring, so it doesn't have any in neighbor coming from the up, but down, its down neighbor is 1. So down, dest neighbor is 1, source neighbor is negative, which is undefined, and sum is 0 because it's never getting anything in because it doesn't have any source to pass into it. And so it's the same for pretty much all of the other ones. If we just look at the sums, so this is the sum along the first row. This is 22 because all these numbers get summed up this way. And this is 26 because all these numbers get summed up. And if we look at, say, this one, then this one, the sum should also be 0, which it is. But this one, the sum is 1 because eventually it does get the rank 1 passed in that way. Any questions? Go ahead. Mm-hmm. Yeah, so there are 2 questions. One was, let me make sure I get this right. So one was about like which direction is the displacement going in? Yeah, so for dimension 0, displacement 1 is to the right, displacement negative 1 comes in from the left. If you want the other way, you could like set the displacement to negative. Yeah, and then in the vertical direction, displacement 1 is down, displacement negative 1 is up. You're passing this way. And second part was it chose the dimension lengths for us. Like here in this case, it's 4 by 3. I think the dimension length is somewhat independent of the periodicity. Like theoretically, you could set, because the periodicity is just, it comes from here. Like you pass it in as well. Actually, I'm not really sure why you would, like it's not so much extra cost to make it a ring. So in any algorithms, you do want it to be a ring. Like if you think about Cannon's algorithm, you have to keep going around. So unless you have a good reason, you might as well just make it a ring. The length of the dimension, I think, is a little bit separate from that, in that, like, it could, theoretically, if it wanted to, it could make it 12 by 1. There's not much point in that, I guess, but, like, it could. And so, But then that would still be a valid thing to do because like you're just getting the dimension here, like nothing is hard coded in. You're just using what they gave you here. And well, we had to set the number of dimensions, like that's you have to figure that out. But the length of the dimension, you just ask for it here, and you just keep using it here. You could also set it like if you know, for example, that you have a square, you could just manually set the dimensions yourself to root p by root p, and then you would just pass it into card create. Other questions? Yes. In a Cartesian topology, is the number of dimensions always 2? For the MPI purposes, it can be arbitrary dimensions. Like here in cart create, for example, we pass an ndim. This example, it's 2, but it could be anything. Or I guess it has to be greater than 1. Or sorry, it has to be at least 1. Because sometimes algorithms can be expressed easily. Like we have been doing matrix algorithms, which are easy to express in 2D, but sometimes you may have a 3D input, and so it may be easier to express the grid as 3D as well. Other question? Okay. Yeah. So that's Cartesian topology, and that's one of the useful ones because then it avoids having to actually like figure out. You always have to figure out your neighbor. The most general way. So in general, topologies are just graphs. Like, and some graphs are easier to think about in the context of some problems than others. But in general, every topology can be represented as a directed graph with multi-edges. And so similarly, in MPI, the most generic way to describe a topology is also with graph format. Yeah. So we're going to talk a little bit about graph representations. So the most basic way that we learn about how to represent a graph is called adjacency matrix, which is if you have n vertices, you represent your graphs using an n by n matrix, which is a square. And if it's undirected, it's unweighted, then it's binary. 1 means that there is an edge, 0 means that there's no edge. And if it's undirected, that means both, like if there's an edge, then it goes in both directions. So the thing is symmetric. If there's an edge from u to v, then there's also an edge from v to u. And so that's why it's reflected across the diagonal. So this is just an example. We have this graph. We represent it like this. And you can extend this, like if it's directed, which means that it's binary, or it's directed, but still unweighted, so it's not symmetric, then it's no longer necessarily it's no longer symmetric across the diagonal, but it's still a matrix. And you can also make it weighted, like if they're not binary, but they can now hold weights. Yes. Yes, if every edge was bidirectional, then it would be the same representation as the undirected graph. It's just that in directed, it's not necessary that it is bidirectional. And we can also easily extend this to weights. Rather than storing 0 or 1, you can just directly store the weight in the matrix. So, are people familiar with this? That's good. Yeah. In reality, most graphs are sparse, which means that they have many less than n squared edges. So like the most edges you could possibly have is n squared because you have an n by n matrix. But in practice, like most of the edges are not connected, or sorry, most of the nodes are not connected to most of the other nodes. the meaning, like if it is dense, which means that you have close to n squared edges, that means almost everyone is connected to almost everyone else all the time, which is not really true in practical scenarios. So people have come up with these specialized representations for what are called sparse graphs. And so one really classical one is called an adjacency list. And this is kind of how you go to it. So you start with this adjacency matrix, which we just did. This is an n squared matrix. And this is always going to take space n squared, no matter how many actual entries are in here. But for sparse matrices, ideally, we would like to use sparse representations, which take space proportional to number of edges plus number of nodes, rather than n squared. Because in practice, if m number of edges is much less than n squared, this whole thing is much less than n squared. And so the way that you do these sparse representations is basically you just take out all the so they call them non-zeros, which are just like the entries that are actually there. And you explicitly store the non-zero coordinates. So like in adjacency matrix, the coordinates are always implicit because the values here, just the adjacency, but could also be the weights, are the actual things that you store. And the actual coordinates, which are like u and v, which are the things that are connected, are implicit in the indexing. Like nowhere are you actually storing the node IDs. You just get them from the indexing in the matrix. But in sparse representations, you actually write down the index. So in the adjacency list, you have basically an array of size n, which is the number of vertices, and each one is attached to a list of size degree of that vertex. And you just write down the neighbors of that vertex. So here, 1 is connected to 3 and 4. You write down 3 and 4. Those are the outgoing neighbors. And 2 is connected to 3, or 3 is the outgoing neighbor of 2, so that's why you write 3 here. And so on like that. 6 has no outgoing neighbor, so nothing is next to 6. So rather than taking space n squared, this takes space n plus m, where n is the number of vertices. Any questions? So the main difference between these, like I said, is in the adjacency matrix format, the vertex IDs are always implicit. You get them, if you imagine indexing into this matrix, you would put like, if you want edge from u to v, you would index like a uv in the code. But here, to access that edge, you would have to look at the list corresponding to vertex u, and then look through it to see if v is there. So the way that you interact with these things looks different in the code. But you can still run the algorithms on this thing. The inner loop just looks different. In reality, the most common sparse representation is called compressed sparse row, or CSR, which is just it's kind of like the flattening of the adjacency list in some sense. So there's in the unweighted case, there's 2 arrays in CSR. One is called index, sometimes called offsets also, and edges. So edges is just like if you flattened this edge part of adjacency list, that's what you get in edges, like 3, 4, 3, 2, 6, 2, 4. This is 3, 4, 3, 2, 6, 2, 4. So you just concatenate everything that you got in adjacency list, just in order. And then the point of index is like, well, if you only had edges, you don't know where the neighbors for 1 and the neighbors for 2, or you don't know where like the neighbors for 2 or 3 or anything like that start, because you only know the beginning. So the point of index is to tell you for some vertex, where do its neighbors start in the edges array. So that's CSR. And it takes space, n plus m as well, because the length of the index array is n, you need 1 entry in index for each vertex. And m comes from edges. Each edge is represented once in the edges array. but you just store the destinations. You don't actually need to store the sources because the source is implicit in index. So the way to get the neighbors of some vertex is similar. Like in adjacency list, first you would go to entry 3, and if you wanted to look at all of its neighbors, you would just look through this corresponding list. In CSR, if you want the neighbors of entry 3, you look at the entry at 3, which is 4, and you go to position 4, and you look through until the start of position 5, in which case you know, or sorry, position 4. So like you know that 4 and 5, which are these two, are the neighbors of 3, and then you stop there. So if you imagine iterating this whole thing, there would be 2 loops, one over index, and one over, let's say the outer index is I, one over index with I, and then one over edges, which is indexed by index I and index I plus 1. And to get the bounds for vertex I, then you look at index I and index I plus 1. Questions? Yeah, so you can see how to convert between these formats. Like let's say you were given something in this form, adjacency list, and you wanted to convert it into this form, CSR. You could iterate through the adjacency list, and you could build edges and index as you go. Yeah, you could also do it in parallel with prefix sum, because you basically are keeping, this is basically a prefix sum on the degrees. So you could do a prefix sum on the degrees here, and then you just in parallel copy in edges and index. What makes this more efficient than using the adjacency list? This is better cache locality than the adjacency list, because if you think about how you would implement this, like in C, you might have like a vector, or C++, you might have a vector equal to length n, and then each one of them could have a pointer to like an STD vector, or like if it's dynamic, you can point to like an STD set or an STD map, and that would be like one pointer indirection to go there. And yeah, but if you wanted to access multiple, so if you're only accessing one adjacency, it's not much better, but if you're accessing multiple, it is better if they're closer together. Okay. One common pattern is that you may have to go through the entire adjacency. So in that case, you're just going this way. Another question? Yeah. So that is CSR. And another form, so the form that you usually get the matrix when you read it from file is called coordinate, or COO, which basically stores all the edges as tuples of source, destination, and weight. And so this is how you would represent this. It's also called edge list. And you could use, yeah, so like if you go online and you try to download these sparse matrices, they come in more or less like this format, one per line, which is source, dest, weight. So here this is the edge 1 to 3, and it has weight 10. So 1 to 3, it has weight 10. Something like that. This takes space 3m, because you write one line per edge, which is m, and then each one of them has 3 entries. That's just another matrix representation. CO is what you get in the file, but sometimes you may want to convert it into something like adjacency list or CSR, because it's not easy to tell where the vertices start in COO. Like if you wanted to ask like, okay, like where are all the neighbors of vertex 3? You could find the start of 3, like you could do some kind of binary search like thing, but it's not as easy as just like directly indexing in the adjacency list or in the CSR. Any questions on that part? Yes. When would you want to use this? If you always know that you have to iterate through the entire thing, then this would be fine because you would just start from the top and go down. If you ever need to do indexing though, you would probably need to convert it into this to be more efficient. This, it's easy. It's easier to understand than the other ones, so I can understand. So I think that's why they put it in the file format. But I think it's just not worse. Yeah, because in CSR, if you wanted to iterate through every edge, like you would have this the two loops, like I mentioned, and then in here, if you want to iterate through every edge, you would just iterate directly through this thing, but you would still have to read both the source and the dist. But in CSR, the source is implicit. Yeah, but maybe one useful thing is like to think about how you can convert between these two. You can always convert between like any matrix format to any other one, but to understand like how the looping pattern goes, sometimes it helps to do this conversion. Any other questions? So that was a bit of an aside, but it is useful because you will have to use it in homework. But anyway, the reason that I brought it up here is because we use these graph representations to represent, because topologies are graphs, you can also use these sparse graph representations to represent MPI topologies. So this MPI general function to create an arbitrary topology basically takes in a CSR. This is a collective, so it's called graph create. You pass in the old communicator, the number of nodes, the index array, the edges array, whether you can reorder, and then you come. And this index and edges are just the same index and edges that are in the CSR representation. It doesn't guarantee anything if you have parallel edges, so you have multi-edges. And I guess this means, like if you, in the CSR, you could put theoretically you could technically repeat an edge if you wanted to in a multigraph, but I don't think it gives you like stronger guarantees about the communication. Yeah. So this is an example. Let's say we wanted to represent this tree. So we have nodes 0, 1, 2, 3, 4, 5, 6. And the neighbors of 0 are 1 and 2. So that's 1 and 2 here. The neighbors of 1 are 0, 3, 4. So that's 0, 3, 4. And the meaning of index is it starts where node 1 starts, because the start of index would always be 0, because the start of node 0 is always at position 0 in edges. Depending on how, like CSR, sometimes you can put 0 in the front, sometimes not, but usually edges of 0 starts at position 0 in edges anyway. So here they just got rid of it, and the start of position, and then you have node 2, which has neighbors 0, 5, and 6. So 0, 5, and 6 are here, and they start at position 5 in edges, and so on like that. So this is like, if you have the entire graph topology, then you can build a CSR, and you just pass it into this MPI function. Yeah, so this is some example usage. So this is how you would create a hypercube topology using this graph functionality. So in a hypercube, depending on your bit representation, all your neighbors are just 1 bit flipped from you. So if you have d bits, you have d neighbors. So number of nodes starts at 0. The com size, you put it into number of nodes. And the number of neighbors is log the number of nodes, because the number of bits that you have is log the number of nodes in the world. And we're going to fill in the CSR. So we have index and edges. So the length of index is always equal to the number of nodes that we have. And here, because it's a hypercube, and we know that everybody has a fixed number of edges, which is equal to k, here set to log number of nodes, then total number of edges is number of nodes times k. Yeah. And we can also set index up front as well, because we know that everybody has fixed degree. And we're just going to go like this. So through the outer loop is through the nodes, the inner loop is through k, and we're just going to fill in the neighbors of the given node. And the way that you can do that is you know what your bit string is. You can make a mask of just one bit, and you just flip whatever bit is at the mask, and you just step one to the right, and you do it k times. And so then we fill it in, edges of position plus plus. Position plus plus starts at 0, and in the end it should equal length of edges. And yeah, then we have filled in index and edges, and we just pass it in to graph create. And that's it. Questions? Yeah, so there's just more general ways to create this graph thing. Like the way that we just did, you have to fill in the entire CSR. You can also, sometimes it will also let you given weights, which is some additional information, like the volume of communication that you expect along those edges. And the most general MPI way to generate these graph topologies is rather than doing like this collective thing, you can do it in some sense like per node. So like each processor is a node, or each processor is a group of nodes. So it's more distributed. So you don't have to like collect the whole CSR into each processor. Yeah. So this is the distributed way to create it. MPI disk graph create adjacent. So you take in, so from this view, each rank is one node in this graph. Takes in an in degree, a list of sources, a list of source weights, an out degree, a list of destinations, a list of dest weights, and some extra metadata, and you get out a new communicator with this graph. And source weights and dest weights are non-negative integers. So this is how you'd use it. So process 0, let's say it represents 0, it has no in degree, it has out degree of 2, and the out neighbors are 1 and 2. So there's no in degree, source is empty, out degree is 2, and destination is 1, 2. Process 1 has in degree 1, out degree 2. The in degree is 1, and the source is 0, out degree is 2, and dest is 3, 4. Okay, this is just like a more distributed way to do it, so you don't have to fill the entire CSR. And yeah, up to P6. And then the most general way to do it is rather than one node per process, you can make multiple nodes per process. And then, yeah, it's similar. Then n is just the number of source nodes. Yeah, so here, if we wanted to use 2 nodes per process, then n would be equal to 2. And the sources are 0 and 1. Yeah, this is representing nodes 0 and 1. Then it gives you the degrees, 2 and 2, and the dests are kind of like in CSR based on the degrees. Any questions? Let's go back. So this is just the most general way of doing the topology creation. Probably they build like card create and stuff like that on top of this, but you can, like for example, we built the hypercube on top of something similar to this, and you can build arbitrary topologies using this, because any topology is just a directed graph. Mhm. Yes, sources is just sources is which node is this. Yeah, sources are like which nodes are represented on this process. So process 0 is representing node 0 and node 1. Process 1 is representing node 2 and node 5. Yes. So here, like 0 has degree 2, 1 has degree 2, but for 2, 5, 5 has no out degree, so that's why its degree is 0. And then 2 is just, of course, like 2 has 5, 6. 2 has 5, 6 here. Other questions? So finally, a little bit about custom operators. So in MPI, we have seen like you have MPI add and MPI multiply and some basic operators. I think they have binary ones as well, like and or, and so on. You can also define arbitrary operators using MPI. So this is just an illustrative example. So suppose that we have an array input A, and we want to, for every entry of A that is 0, we want to replace it with the nearest non-zero element to the left. So you could easily do it sequentially. You just loop left to right, but we would like to do it in parallel. And the way that you can do it is we make a secondary array of tuples for every index I. If A of I is non-zero, then we set a tuple I and A of I. Otherwise, we set a tuple -1 and 0 if A of I is equal to 0. So for these tuples, if A of I is empty, then the first index is -1, otherwise it is I. And then we can do a prefix sum with this tuple and with the modified max operator. So this max operator takes in these two tuples, I of I, J A of J, and it sets if I is greater than J. So this I is the index, and this is I, and this is J. And so it's always going to be greater than -1 because indexing starts at 0. So if I is greater than J, which means that the index that it had in this tuple is just existed, then we set it equal to A of I. Otherwise, set it to J A of J. Yeah. And so we have these MPI functions. Here we're using MPI scan. And then we have these built-in operators like sum, product, min, max, so on, logical or, logical and, binary or, binary and. And the way that you can do it, if you want to define a custom operator, you make a function. Here it's called myOperator, which takes in a vector and an out vector. This is a length, and these are the data types. And this iterates over the length. This is the number of elements of this type, so this is iterating. Oh, this part is the tuple, and in and out is just the input and output arrays. Because 2 times I and 2 times I plus 1. So it represents the tuples. If you have n tuples, it represents the tuples as an array of length 2n. Where it's just like each entry has two numbers in it. Yeah, and this is performing this max operator. So if the max, this is just max. So like if this I is greater than J, so this is I, this is J, then it performs this thing. Yeah, and then the way that it does it, you can define an operator. So we have this function, and you can call op create. So this function pointer here, and then you can pass it into this new MPI op that you created. And that's it. Yes. Okay, so let's go through this. Yeah, I'm just going to go through, and we can read through this together, and feel free to ask any questions. So this is program assignment 3. I guess it's due April 14th. And in this one, we're going to implement sparse matrix multiplication, where both of the matrices are sparse. So that's called SPGEM. There's a version of this. There's like several versions. So we have been doing GEM, which is dense matrix, dense matrix. There's also a variant that's sparse matrix, dense matrix, but here it's both are sparse. And it's on this 2D root P by root P processor grid. So we can assume that we have a square number of processors P, and we'll just use MPI like we have been doing. So there's kind of two main steps. The first step, similar to the algorithms that we have been doing, the first step is first you have to distribute the elements onto the grid. So like if you remember in Cannon's algorithm or in Summa, first like Pij needs the entry Aij, Bij, Cij. And so the first step is to just distribute the entries onto the processor grid. And the next step is to actually do the multiplication with, here we're going to implement Summa. And in addition, we have provided this code. So you can implement all paired shortest paths with just matrix multiplication. And so we wrote some outer code to implement APSP using the sparse matrix multiplication. And you can do it just directly with a translation. You just need to change the functions, or you need to change the operations that are used. So in a normal matrix multiplication, it's like you do a dot product with plus and multiply. But in graph algorithms, often there's this connection between linear algebra and graph algorithms by changing what they call the semi-ring, which is by changing the operator. So rather than using multiply or add, you can use some other operators where, and then the entries would correspond to weights in the graph. So this handout is pretty long, but it is helpful. So I recommend that if you have questions, you can look at it first. So SPGEM is a variant of matrix multiplication for sparse matrices. So we have been doing sparse matrix representations, and in sparse matrices, most of the entries are 0. And like, so the point of sparse operations in general is one, that you want to save the space to store space proportional to the number of edges or number of non-zeros, but also to save work. So in dense matrix multiplication, the work is always n cubed, where n is the length of the matrix. But in sparse matrix multiplication, you can take time proportional to the number of non-zeros you have. So not only do you save the space, you also save time by only computing on non-zero entries. And the way to do that is by writing these algorithms to use the sparse representations. So earlier we were talking about CSR and adjacency list and so on. The algorithm should iterate over sparse representations like CSR or adjacency list or whatever you choose, because those iterations should only iterate over the entries that are actually there. And the only entries that you're going to multiply are entries that are actually there, because the point of sparse operations is that like you skip over the zeros, because zeros will, you could multiply with 0, but it wouldn't add anything to the output. So we can skip that. Okay. Yeah, so this is just saying the difference between SPGEM is different is that most of the entries are non-zero, and so it reduces both the computational complexity and the memory usage, and it relies on these sparse representations that only store non-zero entries. And the challenging part in SPGEM is that you never want to, ideally, you never convert back into the dense format. So ideally, you want to run the algorithm so that both operands A and B and the output C always stays in a sparse format. Questions? So we are going to implement SPGEM using sparse summa. So the high level of sparse summa looks exactly the same as dense summa, like we had done last time. It's based on outer product, you iterate over k, and yeah, the thing, like the blocks that you broadcast are the same logical blocks, they are just now sparse. So we're going to do C equals A times B. They're all matrices. Matrices A and B are given in CO representation because that's how we read them from file. And so in C++, this is a vector of pair, or a vector of pairs where the first entry is also a pair and the second entry is the weight. So it's like more or less like a 3-tuple row column value or row column weight. And this CO representation only has the non-zero entries. And then once we finish, we also want to get back out matrix C in COO form. So we did some sparse representations. You'll get the input and we want the output in COO, but you can convert it into whatever intermediate format you like if you find that it does better. And yeah, so there's two. So the most basic way that we test it is we just directly do the sparse matrix multiplication. And assuming that A is square, we can do A times A transpose. And the inner dimension should line up and we can do the multiplication. And ideally, the SPGEM should work for any rectangular matrices. And that should work because summa works for non-square matrices. And I drew this picture to illustrate what is going on. So let's say we have a 3x3 grid. We have matrices A, B, and C. Let's say the block size is B. And we're going to do 2D partitioning, which is that you cut, if you think of it, it's easiest to like logically think of it in the dense way. So like you have n by n matrices, you're going to cut the matrix in like n by b into n by b block rows and n by b block columns, where every tile is, or every block is size b by b. But the number of non-zeros in that b by b section is much less than b squared. So this is just an illustration of the initial configuration of the distribution. So this is processor 0, 0, and I use the colon notation. So this is A 0 through B minus 1, rows 0 through B minus 1, columns 0 through B minus 1. And that's the same for A, B, and C. For processor 0, 1, the column changes. So the row stays the same, is 0 through B minus 1. The columns are now B through 2B minus 1. And then so then this last one changes, 2B to 3B minus 1, and so on. And then the different rows, now the row range also changes. Here, B to 2B minus 1, here 2B to 3B minus 1. So the first part is you get the thing in COO, and somehow you need to figure out so you have a list of non-zeros, and now you have to figure out where are those non-zeros going according to this initial distribution. So that is the initial configuration. And this is the pseudocode and the same picture in the slides that we had for Summa. So we have some block size, we have some processor rows. Block size is just n over processor rows, which is root p. And we range over k. So for k0 up to processor rows, we broadcast the column k of A along the processor row. We broadcast the row of B along the processor column, so like this and that. And then you do the Cij. So the broadcast part should be hopefully once you cut the tile correctly, the broadcast part is just broadcast. You know how big the tile is, and you just broadcast it along the row, or vice versa along the column. So that part should be mostly straightforward. Another subtlety. So the first part is the distribution. Then the broadcast is probably the easiest part. And then the next part is once you have the tile of A and B that you need to multiply, you have to figure out how you're going to do this local multiplication. And there are many options for how you do this local multiplication. So it depends on the format that you got the A and B tile in. And you also don't, like the whole data flow on the very highest level is based on outer product. But all you need to do is multiply this tile of A, some tile of A with some tile of B. And on your local process, you can do it however you want. Like it can be with outer product, it can be with inner product, it can be whatever. It just needs to output the tile of C in the correct form. And you need to keep around a standard represent. So like the tile of C is going to get modified through the rounds of Summa, because you're going to get more and more non-zeros into C as the rounds go on. So it needs, this is probably the most challenging part of sparse SPGEM, which is that you don't know the non-zero structure of C up front. And so you need to keep some type of representation that can accommodate changes to the non-zero structure of C. So the most straightforward way to do this, you can use like C++ built-ins like set or map, for example. Later on, you could, if you have time, you could think about more optimized versions. Does the challenge make sense? Like, is it? Maybe I could say it again. That would help. Yeah. So just forget about the tile thing for now for a second. Just think about general SPGEM. So you have a sparse matrix A, say in CSR, and you have a sparse matrix B in CSR. And in outer product, you're trying to, let's just do it in inner product for a second. So you want to make one entry, it's just an outer product actually. Okay, so you're trying to multiply like a column of A with a row of B, and you're doing this like outer product thing where you get this partial thing that you're trying to stack onto the output C. And that partial of C has some non-zero structure, but many of the non-zeros are not there because it's A and B are sparse, so the output is also sparse. It's not always true that if both are sparse, the output is sparse, but it's likely that this partial of C is sparse. And okay, so let's say, but you don't know where the non-zeros are. You're only discovering them as you do the multiplication, because you have the column of A and the row of B. And so you know that like if you have some AIK and BKJ, then you get an output CIJ. But in the beginning, you don't know where the CIJs are. So one easy way is like you keep a list of per row, let's call it like STD map, where you store the column ID and the value. And somehow you need to be able to retrieve those again. Because now when you get a new column, even in the same column, doesn't matter, you have a new column of A or a new row of B. Now you get a new partial of C that may or may not have the same non-zero structure as the previous partial sums of C. But you need to collapse that into what you had from the previous multiplication addition. And so if you had this vector of map, now you can update it, but like it is not it's not so straightforward as having like a 2D array and indexing into it. Does that help? Yeah, I would suggest an initial implementation just to do like something like a vector of map, because that will straightforwardly allow you to modify the non-zero structure, and then later on you can do further optimization. But at least it's good to get something working first, and then you can change it. Yeah, and then the second part is just talking about all pair shortest paths. So our all pair shortest paths is you have a graph, and you want to find the shortest path in the weighted graph between every pair of vertices. And weighted graphs are just every edge between the vertices has some weight, and here we're going to assume that they're non-negative integers. And then a path is just a list of vertices where there's an edge connecting every consecutive pair of vertices. And then you don't have to figure out how to implement all pair shortest paths using SPGEMs. That is already given. The only part that you have to figure out is which operations, how to change the semi-ring operations to use in SPGEM to implement APSP. So if you look at the code, you may get a clear idea, but basically the way this works is that APSP can be implemented by repeatedly calling SPGEM with some operators. You don't have to figure out that outer part of like how many times you need to call SPGEM to solve APSP. That is already done. Only the operator needs to change. Like by the operator, I mean in regular matrix multiply, you do plus n times, but you can change it to be arbitrary operators. Like it could be like any of the MPI operators or any arbitrary operator, like min or max or whatever it is. Plus, minus, divide, something. Yeah. So there's a chapter in CLRS, chapter 23. The book is on Canvas, and that should explain in great detail about APSP. And so this part is now explaining the code framework. So the code is at Git, and yeah, so you have to submit 3 files: SPGEM, SPGEM CPP, which is where you implement the SPGEM, APSP, CPP, and distribute.cpp. So distribute.cpp is the code that does the first step of separating the non-zeros into the grid. And then some things that don't need to change. There's a test driver. The test driver does the file IO. This is just give the function signatures. And then there's a file on Canvas with the input files. So you can just download that from Canvas and unzip it in the top level directory of PA3. Yep. And this is just recommending the directions to go. So download the code, look at the code, implement the things first in distribute SPGEM, and then in APSP, you only need to change the operators. And there's also validation code in the test driver. So in the inputs, there's also output validation or like results validation as well. You can also write your own, like you can put in whatever inputs you want, but then you have to write the output validation as well. There are 3 files, and these are the function signatures. So the first one is distribute. Distribute takes in M, N, which are the matrix dimensions, the full matrix. So this has the format, you have a pair where the first entry is a pair and the second entry is an int. This is row column, this is weight. And then you get in this full matrix, and you want to get out on each processor a local matrix of the block, like in this picture. every process should get its own A, B, and C. And so you just call this for each A, B, and C. So you get in the full matrix, you get out the local pointer to the local matrix. There's a root and the communicator. And this one, you distribute the non-zeros of the matrix. And the communicator will be given in the Cartesian topology, like we have just been doing. Yeah, and the processor grid is square. So you can use functions like cart rank and cart chord to determine where you are in the grid. Yeah, and in the beginning, we will just do the file I/O on rank 0. Then the second part is to do the SPGEM. So it takes in M, P, and N, where M and N are the outer dimensions, P is the inner dimension, and we have matrices A, B, and C. A and B filled in, C is something that you have to fill in. And this is what I was talking about. You can define arbitrary functions. So this is how you do it in C++ with std. So this is plus, this is times. And for regular matrix multiplication, it's just addition and multiplication. But these are arbitrary binary operators. Like in this function signature, they're called plus and times. But like you could pass in, for example, like min as plus. And then it would just run the same flow, but it would apply a different operator. So yeah, they have this format, the same COO format, A and B, and then C. And so you get a row communicator and a column communicator, and that is to perform the broadcast in Summa along the row and along the column. So we already did that. You don't need to do it. It's easier because, like, if you think about how you would broadcast along a row and along a column, in the beginning there's only the 2D grid, but you want to basically we make subcommunicators for the processor rows and the processor columns. So that part is also already done. Yeah. And this last one, JPSP takes in the number of nodes, the graph, the result, which is also a graph, or a 2D matrix, row communicator, column communicator. And then the code is there. I will show it in a second, but you only have to change 2 lines. The APSP is already implemented. And then the input data, the inputs come from, this is like a really common matrix input collection. It's called sweet sparse. So in sweet sparse, there's many matrices that come in the file form like COO. We just downloaded a couple. And they look like this. So row, column, weight. So this is A01, the weight is 2. Yeah, so we modified slightly the input data. So from sweet sparse, you only get the matrix structure. And however, to do the validation, I think we also put the answers in the input files. So that's why they're pretty big. So there's multiple ways that we could be possibly doing the validation. One is that we rerun this. So like somehow you need to validate the SPGEM against the correct SPGEM output. And one way to do it is to like build another SPGEM. And another way to do it is to put the output in file and then cross-check the file with the output of the computed SPGEM. Yep, so it also has the correct outputs in there. Yeah, the rest is mostly similar to previously. There are 3 files, there's a report, and then there's this point breakdown, which has some times. Yeah. Questions? Yeah. You would probably change it in SPGEM because if you look at the function headers, SPGEM takes in A, B, and C in COO format. Yes, like distribute takes in a full matrix in COO, and you get out the local matrix also in COO. So this is like the thing that you can pass in to A, B, and C. And then in SPGEM, you can, if you want, you can convert it into a different format. Not that much time, but we can really quickly look at the GitHub. So this is GitHub. Oh, let me zoom in. Okay. So we don't need to go through all of this because like some things you don't need to change, like PA3 doesn't change, but we can start with distribute. So distribute just has this function header that we just looked at, and full matrix, local matrix, root, and the 2D communicator. And APSP. Yeah, so this APSP code, it calls SPGEM2D, which is the function that you will implement. And this outer part, you don't have to change it at all. The only part that needs to change is here. This return 0 should not be return 0, it should be something else. And we can look at an example. So let's look at PA3. Okay, so there's a couple of tests. So there's two tests. One is SPGEM and one is APSP. And if the test type is SPGEM, the first step is to distribute the matrix, E transpose as well. And then if the test type is SPGEM here, then it calls SPGEM2D with A times A transpose. The result goes into SPGEM result. And here you can see an example of how to implement these operators. So this A and B, you just return plus A plus B. And this A and B, you return A times B. So this is defining addition and multiplication in the operators. So in APSP, that was return 0 for now, but you have to fill it in to something else because it's not right to return 0. But just to fill in for now. And yeah, you can look at this. It's like, this is just using the functions that we did in class. So like cart create, for example, and then cart get and com split and stuff like that. And so com split is how we get every processor row into its own communicator and every processor column into its own communicator. Yeah. And I think I'm out of time, but feel free, like when you look at this and you have more questions, I'm sure they will come up. You can ask in the office hours or on Ed. Yeah.